So today we want to look at the electrical power system with a view to understanding all the components of the power systems and also how the components in the power systems they interact with one another. We are also going to see in details, brief details, each section of the power system, and we are going to see what a power system really is. So when we say power system, we know you already have an idea of what a power system is at the back of your mind. But let us look at the objectives of this particular program, because your appreciation of the power system will enhance your knowing what to do as a maintenance technician, as an electrical maintenance technician, because you will come to appreciate the various levels of voltages and the various equipment that will operate or work in these various levels of voltage. So what are the training objectives, the objectives of this very program? First, at the end of this program, you should be able to appreciate all the components of the power system, all that is contained in the power system. And then you will also understand what electrical power system really is. Then secondly, you will appreciate, like we said earlier, the various voltage levels, okay, that you will come across in the various sections of your power system. And finally, we will see how the components of the power systems, as we said before, how they interact to ensure that you get what you actually want from your power system. And your understanding of the electrical power system and the various levels of voltages that are in the power system, and also the various power system components, will improve your understanding and ability to carry out your job or your job role as an electrical maintenance technician, as we said earlier. So to help us to achieve all of these objectives, we have broken down this program into a series of topics or modules. So first in the topics is that we are going to introduce ourselves into what the power system is and the various power system components, the electrical components that we will find in the power systems, and what they do in the power system. That is the first part of the agenda that we are going to handle. Then secondly, in the power system, we'll come to see that one section of the power system is the generation system. So these generation systems, what are the equipment that we can find in the generation system and how they work? We are also going to see all of this so that our appreciation of it will help us to carry out maintenance and operations in our power system. Then we will also see the second section of the power system, which is the transmission section, because we know that whatever that is produced or generated at the generation station must be evacuated to your point of utilization. So we are going to see the transmission system components, as in the equipment that you. Then of course we are going to see lastly the distribution system. We'll look at the components of the distribution systems, the various equipment we will find in distribution systems, and how we can better operate and maintain the distribution system. We are also going to consider all of this. Okay, so most of the components and equipment that we are going to discuss, though we are going to briefly tell us, okay, in this particular program. We have other training on electrical machines, though that particular training explains in details these various components, how their principles of operations, their physics of operations, how the various components found in them interact to actually give us what we actually need from these equipment. So in this particular training, we are going to see the power system generally and the various sections of the power system, and also the equipment that we'll find in these various sections of the power system. Okay, so we are going to start with the first part of the power system, which is the generation station. So the power system generally, let us just briefly define the power system before we go into these various sections and components. So the electrical power system is a network of components and equipment that is meant for the production, the transfer, that is the supply, and the utilization of electricity. So when we mention the power system, we are talking of everything from generation to the point of utilization. So the power system comprises of the generation system, the transmission system, the distribution system, and the consumer system. So the first part of it is the generation station. So as the name indicates, that is where the electrical energy or the power that we need in our system is produced. So that is where it is produced. So in our environment here, most of the power stations that we have, they generate electricity at 11 kV, as you can see on your screen. Okay, that is 11,000 volts or 11 kilovolts. So that is the function of the generation station. Later in the course of this program, we will see the components, okay, the equipment that we can find in the power generation stations or plants. Okay, so immediately following the generation station, remember, all we have to do at the generation station is to generate the electricity that we need. That electricity will not be used at the generation station. So we need to move that electricity from where it is generated to where it will be used, which may be several hundreds of kilometers away. Okay, so with the whatever that is generated will now be sent, as you can see also, to your transmission system. And the first part of your transmission system is the switchyard. And the first component in your transmission system is the step-up transformer, okay, or the transmission transformer, as you can see on the screen. So the function of that transformer is to step up the input voltage from 11 kilovolts to about 330 kilovolts, okay, because here in this particular country, 330 kilovolts is the highest transmission voltage that we have. So that 330 kilovolts will now be sent from your switchyard into your transmission system. So the transmission line, as you can see, it is actually transmitting at 330 kilovolts. So that 330 kilovolts is now sent to a sub-transmission station, okay, as it is getting closer to where it will be used. So that sub-transmission station takes it down from 330 kilovolts to 132 kilovolts. So that 132 will now also be sent along the transmission line, which is the sub-transmission line, okay, to your another substation. It is actually a transmission substation because that is where the transmission line ends, okay, or the transmission section of the power system, that is where it ends. So there we also have a step-down transformer that will take the voltage from 132 kilovolts to 33 kilovolts. So from here, what we have, which is the 33 kV, will now be sent to your injection substations. Okay, so at the injection substation, we also have a step-down transformer, as you can see on your screen. That step-down transformer, what it does is that it will now take the 33 kV that is sent into it to 11 kilovolts, okay? So that is the injection substation. So that 11 kilovolts is what will now be distributed into the various streets and where your load, okay, your consumers are. So that is what you can see. From that 11, it goes to the distribution pool of facilities, and then to your lower distribution transformer. Okay, so we have from here, from the 11 kV. Okay, this is the first distribution level. Then here, this transformer will take it from that 11 kV to about 415 volts. It is that 415 volts that will be used, okay, by your consumers in their various facilities. So if we have other consumers too, okay, that also needs that 415, both commercial and residential consumers, they will be tied to that injection stations, as you can see. So at the consumer level, okay, or close to the consumer or where it will be used, a step-down transformer is always there to take it from 11 kV to about 415 volts. These are mostly the transformers you find at your street junctions, okay, or closest to your load. So there are some consumers that will need higher voltage also, okay. So those consumers, like the industrial consumers, they take directly from the last point of your transmission station, which is at the 33 kV point, okay? They take it straight to your industrial users. So in that, as you can see on the screen also, so in that environment, they may have equipment that uses 33 kV, or they will have their own separate step-down transformer that will take it from 33 to whatever voltage level that they may be needing, maybe 6.6 kV, 11 kV, 3 kV, 2 kV, and of course, lower voltage 415 for their offices and what have you. So now, The purpose of us highlighting this to you is for you to appreciate the power systems components, okay? That is the various sections of the power systems and the voltage levels of each of these sections of the power system, okay? So now let us have a brief review of what we have on the screen. So now the power system starts with the generation station, and the generation station generates at 11 kV. That 11 kV is sent to your switchyard. At your switchyard, it is that's the transmission transformer closest to your switchyard. It is transformed or stepped up from 11 kV to about 330 kV. That is sent to the highest transmission section of your power system. Then from there, it is sent to the second transmission level, which is from 330, the first to the transformer that will step it down from 330 kV to 132 kV. Then from there, it goes to your 132 to 33 kV transformer, okay? Still in the second, still in the transmission section of your power system, okay? Now, as it goes to the 33 to 11 or the injection substation, so as it goes to the injection substation, it is further stepped down from 33 kV to 11 kV. So it is that 11 kV that is distributed, okay, where it is further stepped down to 415 volts face to face and 220 volts phase and neutral that will be used by various loads. So when you look at it, you'll see that in the generation station, the voltage level there is 11 kV, okay? Then the first transmission station section, we have 330 kV. We have 330 kV. Then the second transmission section, we have 132. So at the injection substation, we have the transformer that will take it to 11 kV from 33 kV. So we have 11 kV on our distribution lines, as you can see, okay? Then as it is going to your load, it is further stepped down to 415 volts, 415 volts, apart from your industrial users, okay? So these are your industrial users, they will definitely have a step down transformer that will take this from 33 to 11 to 415 to 6.6 to whatever voltage level that they are using. So now you are familiar with the voltage levels, okay, at the different sections of the power system. So next we are going to see the generation station, and we are going to see the various equipment that we can find in the generation station. So in the generation station, the most important equipment that you will find is the generator. The generator is the equipment that actually produces the electrical power, okay, or the voltage that will be sent to other sections of the power system. So in the generation station, the principal activity that happens, or the principal function of the generation station, is to convert whatever form of energy to electrical energy. So what the generation station does, simply put, is the production of electrical energy. So in the generation station, we have one equipment that does that conversion for us, which is the generator. Okay, so that is the principal function of the generator. It converts energy from other forms to electrical energy. So what are the various forms of energy that could serve as input into the power system? We have chemical energy, the chemical energy that is contained in fuel, okay, either gas or diesel. It is converted by the mechanical part of your generator in the power station to rotating mechanical energy. So that rotating mechanical energy is what is sent to your alternator, which is this. And it is the alternator that will now convert that rotating mechanical energy into electrical energy. So we'll see later how the alternator does this. Okay. So in the generation stations too, we could also have other forms of energy as input. Like the solar power stations, what happens there is that the heat energy that is contained in the sun, okay, is converted directly into electrical energy by those solar panels that we have in the solar power plant. Then we also have other forms too that can convert the chemical energy that is contained in the fuel, convert it to steam, that is kinetic energy contained in fast-moving, superheated steam. Okay, so he does so by generating steam in a boiler, and that steam that is generated in a boiler will now be sent to your steam turbine. So the kinetic energy that is contained in that steam will now be converted to rotating mechanical energy in your steam turbines. So that rotating mechanical energy that is contained, that is produced in your steam turbine is coupled to the alternator. So the alternator will now convert that rotating mechanical energy into electrical energy. So we also have diesel engine, fuel engine that uses, and even the gas engines that uses reciprocating engines. Okay, so in those engines, like the one you can see, they are reciprocating engine, whether gas, diesel, or petrol. Okay, so what it does is that the chemical energy that is contained in the fuel, okay, is converted by combustion in each of those cylinders. Okay, and then the energy that is produced, the combustion product, will now be converted into the translational motion of your piston. And this translational motion is directly converted to rotating mechanical energy by the crankshaft in the engines. Okay, so that rotating mechanical energy is what will now be coupled to your alternator and then converted to electrical energy at your alternator. So we also have the wind turbine that converts the kinetic energy that is contained in fast-moving wind, okay, into rotating mechanical energy and thus into electrical energy at the alternator also, okay, or by the alternator also. We have hydro power stations, okay. It still uses hydro turbines or turbines, but in this case, it converts the potential energy that is contained in dammed water into rotating mechanical energy. Okay, so as the water is falling, it falls on the blade of the turbine and forces it to turn. So that mechanical energy is what will now be, rotating mechanical energy is what will now be converted to electrical energy at the alternator of your generator. Okay, so these are the various forms of energy conversion that takes place in the generation station. But we want to know that principally at the generation station, other forms of energy are converted into electrical energy. So what you have here now is a gas turbine. Okay, so here is the compressor section and this is the turbine section. So what this does is that it compresses air, intake air, then that compressed air is sent into a section called the combustor, because we have three sections in this gas turbine. We have the compressor section, we have the combustion section or combustor, and then we have the turbine. So this compressed air is now sent to the combustor. At the combustor, fuel is injected, okay, or gas is injected, and then the mixture of fuel and compressed air is ignited in that very combustor. Okay, so when after ignition, the high energy combustion product, okay, the high energy combustion product is now directed through what is called the transition piece onto the turbine blade in the turbine section. So the turbine blade, what it does is that it extracts the energy that is contained in this fast moving combustion product that is directed into it, into to rotating mechanical energy. Okay, so as the shaft is rotating, that rotational energy is transmitted to your alternator once again, and the alternator does what? Does the conversion to electrical energy. Okay, so these are some of the things that happen in the generation station, so that you know. Now you have generated this energy, electrical energy. Obviously, that is not where you want to use that particular energy. You must do what? You must take it to where it will be used. Okay? So that brings us to the second component, okay, that you will come across in your generation station. Agreed, this is the most important component, but it is not the only component that you will find in your generation station. So we also have the switch jars. Okay, the switch jars, they are basically means of switching your power to the next section of your power system. So now what is generated at the generation from the generator will be sent to your switch jar. Then from your switch jar, it could now be sent to your transformers, your step-up transformers. After your step-up transformer in the switch yard, we also have other switch jars. Okay, so the function of the switch jars, they are numerous, as we will see later. They do the switching for us. Okay, they also help us to monitor the circuit. They do the protection of the circuit for us also, and they also help us to control whatever that is happening within the circuit if it is so configured. So you see that the work of the switch jar is enormous in our power plant. Okay, but the switch jar is not only in this section of our power system that you find the switch jar. You also see it in your transmission section of your power system. You see it in your distribution section of your power system, even as far as to where you have your load. Okay, either in your offices, in your homes, or in your plant, you have those switch jars there. Okay, so you will see that the switch jar is also a very, very important piece of electrical equipment in your power system. So next, we are going to look at the component of the power generator, okay, or the basic component of the power generator. So the generator is made up of two major components. That is the engine, which is the part that converts whatever form of energy that is sent into the station into rotating mechanical energy. And then we have the alternator. The alternator is the part that now converts the rotating mechanical energy into electrical energy. So, like we said, the engine is the prime mover, as you can see on your screen. That is a reciprocating engine. Could be diesel driven or gas driven. So this is the part that converts, as we will see later, that converts the chemical energy that is contained in fuel, okay, or in the diesel or in the gas into rotating mechanical energy that is transferred into the crankshaft of this particular reciprocating engine. Now, we also have the alternator. Like we said, the alternator is the part that converts the rotating mechanical energy produced at the crankshaft of the engine, okay, into electrical energy, because the crankshaft is coupled to the rotor of the alternator, and then the alternator, the rotating mechanical energy is transferred into the rotor of the alternator, and then the alternator converts that rotating mechanical energy into electrical energy that is fed out of the alternator. So now let us look a little bit in details the various types of the prime movers that we have in the power stations, and then we'll see briefly how they function, how the components of those prime movers, how they interact and produce the rotating mechanical energy that is so needed by the alternator. And then we'll also look at the alternator, how it converts the rotating mechanical energy into electrical energy that we actually need in that is from the power station. Now let us look at the gas turbines. The gas turbine, basically what it does is that it converts the chemical energy that is contained in the gas, methane gas principally, into rotating mechanical energy. So how does the gas turbine does this? If you look at the configuration of the gas turbine, you will see that it has two major sections, okay? Though it has three sections. It has a compressor section and the turbine section, and also the combustion section, okay? So now what happens is that in the compressor section, air is drawn into the turbine through the compressor section, and then that air is compressed in that compressor section. And that compressed air will now be sent into the combustor. In the combustor, fuel is injected into the compressed air. So the mixture of this compressed air and fuel is ignited in the combustor. So the ignition product, which will eventually have a very high kinetic energy, okay, will now be sent into the turbine section by the transition piece. So as it goes into the turbine section, there are blades in the turbine that helps to extract this kinetic energy that is contained in this high energy combustion product, okay, into extract the energy from it and convert it into rotating mechanical energy. So we'll see how it does so later, okay? So that is the turbine that you can see on your screen now. It is open. So this is the compressor section, and this is the turbine section. So this is the rotor of your turbine, okay? This is the rotor running from the compressor end to the turbine end. So now what happens is that air is drawn into the turbine through this intake plenum, okay? So the air goes into the turbine through the plenum and then to the compressor. So in the compressor, you will see that the air is compressed at the compressor and then sent into the combustion chamber. So here in the combustion chamber, you can see the fuel lines. Fuel is injected into that compressed air. So that fuel air mixture is ignited, okay? So as it is ignited, it burns up, and the combustion product is usually having a very high energy content, okay? So that high energy combustion product is now channeled through the transition piece into the turbine. These are the turbine blades. So as the fast moving combustion product is made to impinge on the turbine blades, okay, the kinetic energy that is contained in that fast moving combustion product is now extracted by the blade and then forces the rotor to turn the way your fan normally turns on being impinged by fast moving air, okay? So that is what happens around the turbine blades here. The turbine blade now extract that kinetic energy and converts it into rotating mechanical energy. So the turbine shaft will continue to turn as long as that hot combustion product comes in. And then once the energy is extracted from that much energy have been extracted from, okay, the combustion product with less energy will now be exhausted through the exhaust of the turbine, okay? So now you will see that what we have succeeded in doing now is the conversion of the chemical energy that is contained in the fuel into rotating mechanical energy. So this shaft, as you saw in the earlier, in this diagram, you see that the alternator is attached to the shaft by this gearbox, okay? So since it is attached to the shaft and since the chemical energy in the fuel has been converted into rotating mechanical energy, this alternator rotor will start to do what? To rotate, since it is coupled directly to this gearbox, which is in turn coupled to the shaft of the turbine. So next, we want to also look at the steam turbine. The steam turbine is another very simple but complex machine. So what happens is that steam is generated at the boiler. So that high energy steam, okay, first, the chemical energy that is contained in the fuel, okay, is liberated by combustion, and that heat is absorbed by water, okay, which means that the chemical energy that is contained in the fuel is first converted into heat energy, and then the heat energy is what will now be converted into the kinetic energy in that fast moving steam, because as the water in the boiler absorbs the heat, it will now evaporate to form steam. And as you heat further, that steam will gain more energy, okay, and then for it to move downstream. So that high energy steam is what is sent into this turbine, okay? So as it comes into the turbine, it spreads to both the left and the right, and then the high energy steam impinges on the blade, okay, the rotor blade of the turbine, and forces it to turn. So as it's turning, the shaft also will be turning, okay? Then one end of it is coupled to a gearbox and then to your alternator, as in the case of the gas turbine. So the next that we are going to look at is the diesel engine. The diesel engine, basically the same thing happens. Conversion of the chemical energy that is contained in fuel into rotating mechanical energy. So how does it do this? So as you can see, this is the combustion chamber. Okay, the fuel is injected into this combustion chamber, and then if it is the compression ignition engine, the fuel is compressed until it is ignited. So once it is ignited, that combustion product, high energy combustion product, forces the piston, okay, to move down. So as it's moving down, that translational motion is converted into rotating mechanical motion by the crankshaft. So at the other end of the crankshaft, that is where our alternator is coupled. So you see that the diesel engine, its major function is to provide that rotating mechanical energy from the chemical energy that is contained either in the gas or in your diesel. So we also have gas engine. So in this case, it's the same thing, it's a reciprocating engine as we have here. But in this case, instead of burning diesel, it is burning gas, majorly methane gas. Okay, so the principles, they are the same. So it converts the chemical energy that is contained in that gas into rotating mechanical energy, following the same principle. Okay, the combustion product forces the piston to turn, to move translationally. Then that translational motion is converted to rotating mechanical motion by the crankshaft. Then the other end of the crankshaft, that is where we now tie our load or our alternator to. So that is how, these are the various types of prime movers that we can see in the power plant. And we also have other types too. We have the hydro turbine, like we said earlier. The hydro turbine, it converts the potential energy that is contained in dammed water into rotating mechanical energy. Okay, so that dam water, as it is released and made to drop from that height, converting that potential energy into kinetic energy, it drops on the blade of the turbine and forces it to turn. So as the blade is turning, you see that the kinetic energy in that dropping water has now been converted into rotating mechanical energy. So it is that rotating mechanical energy that will eventually be converted into electrical energy by the alternator, which is what we actually need from the power station or the power plant. So we also have others that converts the kinetic energy that is contained in fast moving winds, that is the wind turbines, into rotating mechanical energy also. Okay, so like in the other cases, that rotating mechanical energy will eventually be converted into electrical energy. So we have seen the various types of prime movers that we can find in the power station or power plant. Now let us look at the electrical part of the generators, which is the main part that converts the rotating mechanical energy into electrical energy, that is the alternator. The alternator has two major components or parts. Okay, so the two major components of the alternator, they are the field winding and the armature winding. So the field winding is the part of the generator that produces the magnetic field, rotating magnetic field. While the armature is the part that produces the voltage or the EMF, okay, that will eventually send from your power station into your transmission line and into your distribution system. So the armature is the part that the voltage is induced into. Okay, so we will see, as you can see on your screen, these are the major parts of the alternator. Okay, we have the armature. So on this particular generator, we have the stationary armature. The armature is usually wound on the stator. Okay, so it is here on the stator. Then the feed winding, that is it on the rotor of this particular alternator. So this particular alternator is a rotating field generator or alternator, because the feed is on the rotor or the rotating part of the generator. Then like we said earlier, the feed is the part that produces the magnetic field. Since it's rotating, as we'll see earlier, because we need rotating magnetic field to induce voltage into the armature winding, which will eventually be sent to these output terminals where your power output will be taken to your transmission transformer and then into your transmission lines. Okay, so now, since what we have here is not a permanent magnet, it is an electromagnet, which means we need a DC voltage to magnetize these feed windings. Okay, because that magnetism is needed to induce voltage into our armature. So now, how do we achieve this? If you look at the screen, you will see that we have what is called the exciter. Okay, so this is the exciter unit. It's like a smaller generator within the big generator. Okay, so here we have the exciter armature, and we have the rotating exciter armature, and then we have the stationary exciter field. So what happens is that the voltage that is produced in the exciter armature, okay, is sent to this rectifier, since we need DC voltage at the main feed winding. So it is sent to this rectifier. So the rectifier does the rectification to DC voltage, okay, or conversion to DC voltage. So it is that DC voltage from this rectifier that will eventually be sent to the main feed winding. So when the main feed winding is magnetized, when the main feed winding receives that DC voltage, it will be magnetized. So once it is magnetized, since it's rotating, it will now be able to induce that EMF that we so require into the armature. So this end of the shaft is connected to our prime mover, any of them that we earlier explained. Okay, whether your gas engine, your gas turbine, your diesel engine, or your steam turbine, whichever. So that is what happens. Then this exciter, like we said earlier, is a smaller generator, which means that its own feed also needs a DC voltage supply. So the feed winding, okay, the feed winding receives its own DC voltage supply from this unit, okay, that is the AV arrow. So the AV arrow receives its power from the output of the generator, and then it converts it into the DC voltage that is so required by the exciter feed. Okay, so that will now help to magnetize the exciter feed. In this case, instead of us having a rotating feed, we have a stationary feed at the exciter. Okay, so as the feed is stationary, but the armature is rotating since it is wound on the rotor. So as the exciter armature is rotating, voltage is induced into the exciter armature, which will now be converted to DC voltage by this rectifier. So this is a kind of showing us the relationship between these three components that we have so discussed: the armature, the feed winding, and the exciter. So this is it, as we explained earlier. So this is the stator. Okay, on the stator we have the armature winding. This is the rotor. On the rotor we have the field winding. Okay, now this is the exciter. This is the exciter armature, and this is the exciter. On the exciter section of the generator. So now you can see that the AVR receives its power from input power from the output, okay, of the generator. So this input power is taken to the AVR, and then the AVR converts it into DC, okay, plus and minus, which is now sent to the exciter field. And then the exciter feed, having received this DC voltage, will now be magnetized. So after magnetization, it will now induce voltage into the rotating armature, as we explained earlier. So once the rotating armature produces that voltage, it now sends it to the rectifier or the diode plate, okay? That is the rectifier assembly that is on the front of the alternator. That will now convert it into DC that will eventually be sent into the field winding. So that field winding that is magnetized, since it's rotating, it will induce voltage, okay, or EMF into the main generator armature, where we eventually get our output from. So if you look at this, you'll see that we have what is called this exciter is called the rotating exciter unit. Okay, there are some generator, and remember this generator too is a rotating feed generator. Okay, there are some where we have the feed to be stationary, like we said earlier. Also, it is fed from the exciter transformer, then it now converts whatever that is fed into it into regulated DC voltage that will now be sent to the feed by slip rings. Okay, so in that case, the kind of generator that we'll be having will not be brushless like this. Okay, it will be having the brush type excitation system. Okay, so we have another training on you can check out for more on this. You can check out our training on generators, okay, the alternators on electrical machines, where it is explained in details. Remember, this section is for us to appreciate what we have in our power system. Okay, so we're kind of explaining it so that you appreciate how these various components of the power system, they function, how they interact with one another. So that is what happens in the alternator to produce the voltage that we so require from our power station. Okay. So let us remind ourselves briefly of how electricity is generated. We want to go into the simple physics of electricity generation as a simple reminder, your elementary physics. Okay, so we know that for electricity to be generated, we need a magnetic field, we need a conductor, and then we need relative motion between the conductor and the magnetic field. Okay, so it depends on how you combine all of this. So once they are properly combined, you will definitely get your the voltage out of your unit. So as you can see, this is what is producing the feed, and that is what we have in our generator feed. But in that our generator case, what we have was an electromagnet. So this is like a fixed magnet, okay, telling us how it is simply generated. So the magnet, you can see the magnetic field running from the north to south pole. That is one of the components we need to generate electricity, the magnetic field. Then the next, like we said, is the armature, the conductor. Okay, this is the conductor, as you can see. Okay, this is the conductor. Okay, so the conductor A, let's say CDAB, okay, to these two slip rings. Okay, we will explain the function of the slip rings later. So that's the conductor, and this conductor is what will now form the armature in your generator, as we explained earlier. Okay, because that is the part that your electricity or EMF is induced into. So now, what happens is that this magnetic field is stationary. We don't have it rotating. But this our conductor, CDAB, okay, can be made to rotate within the magnetic field. So from your Fleming's left-hand rule, you know that once a conductor is made to move in a magnetic field, voltage is induced into that conductor. Okay, so the direction of induction of that current is what Fleming left-hand rule will help us to determine. Okay, so which means that in one instance you have, since it is rotating, in one instance it is moving DC, in another instance, that same instance, it is moving AB. So when AB comes up, instead of it flowing backward, it will be flowing forward. Okay, so which means that we will be having that induced EMF alternating directions. Okay, from forward in the upper part of the circle to backward in the upper, or downward in the downward part of the circle. Okay, so we'll now be having alternating voltage, which is what we actually want. So the slip ring is the means by which we evacuate whatever that is generated in the armature, okay, out to our load. So this could be our load, or this could be our load. Are we getting it? So now this kind of arrangement is known as the stationary feed, because we have the feed now. Okay, these are the feeds stationary on the stator. Then we have the rotating armature, and then we are now evacuating the power or the electricity that we generated from the armature through the slip ring. Okay, slip ring and brush arrangement. Okay, as brushes. Okay, so that is how electricity is generated. So know that in generating electricity in your generator, three components are required: the magnetic field, which is this one that is running from north to south. We need the conductor, and then we need the relative motion, and that is what is manually provided by this cranking handle, okay, to turn. Okay, so in our power station case, the rotating motion is provided by our prime mover, the diesel engine, the gas turbine, or the steam turbine. Okay, whatever prime mover that you are using. Okay, so that provides the rotating mechanical energy that helps to create that relative motion between the conductor, which is the armature, and the field, okay, which is the magnetic field that will be generated or created by or produced by the main field winding of your generator. So that is how electricity is produced, okay? So you need to put it at the back of your mind that these three components must be present. So when you are not having production of electricity in your facility, it means that one of these three components is missing. Either the magnetic field has failed, or the armature, the conductor, has failed, or there is no relative motion. Okay, so whichever that is missing during your troubleshooting, you can detect that at. So let us look at the construction of these alternators now. The construction of the alternators. So in most cases, we'll see that most of the alternators that will come across, they are the rotating field alternators, which means that the stator is carrying the armature. That is the area where we get our main power supply from. Okay, so this armature, you see that they are designed on wound in such a way that the three phases, they are equally separated from one another. Okay, they are placed in the stator slot such that they are separated by 120 electrical degrees from each other, from one another. Okay, so that is what you are seeing here now, and that is what we have here. They are wound on the stator. Okay, so the three phase, one will be the red phase, the yellow phase, and the blue phase. And like we said, the three of them, they are separated by 120 electrical degrees. So which means, and they are wound with the same number, that is the same size of wire, okay? Insulated copper wire, the same gauge of wire, the same number of turns. Are we getting it? So that what is produced in each of these set of windings, the arrow, the red phase, yellow phase, or blue phase, they are the same thing, okay? So now if you look, you also see that we have the rotating field in the middle. So we also have windings in the rotating field. Are we getting it? So to magnetize this, we need DC power supply from the excitation circuit. So this one is on the rotor. So this is a rotating field generator. So once you have your DC voltage sent into the rotating field, okay? Remember, this rotating field is coupled to the prime mover. That is the rotating mechanical energy. So as the field is rotating relative to the armature windings, you see that voltages will now be induced into these armature windings. Equal, since the windings are of the same wire gauge, the same number of turns, you see that equal amount of EMF, which is this, okay? They are induced into the red, blue, and the yellow phase. So you can see the separation, 120 electrical degrees. And since they are equal, you see the amount of voltage, okay, that is induced on each of them, that they are the same thing. So this is how the alternator helps us to convert the rotating mechanical energy that is produced by the prime mover, whichever prime mover you are using, into electrical energy. Okay, so this is the three-phase output that we will eventually get out of the armature. Okay, and this one will be available at the output terminal of your generator, which will eventually be sent in your power station which will eventually be sent to your transmission transformer, okay, and then to your transmission system. But know that, so we need a switching system to switch between the generator and the transformer, and between the transformer and your transmission lines, okay? So like we said earlier, that is the second component of the generation station, okay? Second most important component, which are the switch gears. So your screen now, this is the router to this, okay? This one is carrying the field windings. This is the exciter armature, okay, which produces this EMF that is sent to the field winding. Okay, so as the field is rotating within this, that is, as the field is rotating, you see that since the field is cutting across all of this conductor that makes up the A, B, and C phases, okay, voltages are induced into those conductors. So here we can see a coupled alternator. So we have the feed winding, this is a complete alternator, okay? So this is the part, this plate is what is coupled to the flywheel. If it is a diesel engine, diesel-driven engine, okay, or gas-driven engine, or steam turbine, or what have you. So here is, if it's a steam turbine, here is coupled to the shaft that comes out of your gearbox. If it's a gas turbine, the same thing. If it's a diesel engine can run 1005. Here can be coupled directly to the flywheel of your diesel engine. If it's a gas engine, depends on the speed of the gas engine, can either be coupled directly or will have a reduction gearbox arrangement, okay? So that reduction gearbox arrangement will now reduce it to the required speed that we need. If it's 1005, to take it to 1500 RPM, that will be required by So we have seen the first part of the power system, which is the generation station. So next, we want to look at the second part of our power system, which is the transmission system. Like we said earlier, the electrical energy that is generated at the generation station, we need to move them or evacuate them to where it will be used. So the first section after the generation station that the generated voltage will come to is the transmission system or transmission line, okay? So as you can see on your screen, remember our generation station is generating at about 11 kV. So we will need to move that to where it will be used. I would say we need a transmission line. And then if you look, you see that we have a step-up transformer. If you are not too familiar with these circuit symbols, you should check out our training on electrical diagrams, where the various symbols that are used to represent electrical components and equipment, they are clearly explained, okay? So at the generation station, it generates at 11 kV, and then we have a transformer close to the generation station. Like we said earlier, is the beginning of the transmission system, and that will now take the voltage from 11 kV to about 330 kilovolts, which is the transmission voltage. So later in the course of this section, we will see the reason why we need to transmit at that very high voltage, okay? So as it is moving closer to where it will be used, it is stepped down from 330 to 132 132 kV, okay, in the secondary transmission system. Okay, so as you can see on your screen, this area is the primary transmission system. Then we have the secondary transmission system also. Now, the 132 kV is further stepped down at another substation from that 132 to 33 kilovolts. Okay, so that is the end of the secondary transmission section. So the 33 kV is sent to an injection substation where it is further stepped down from 33 to 11 kV, as we explained earlier in our introduction to power system, the first part of the first session of this particular training on electrical power systems. So when you look, the injection station has a transformer that takes it from 33 to 11 kV, and then that is the beginning of our distribution system. And then we have closer to our load transformers that will take it from that 11 kV to 415 volts or 415 volts, which will later be fed to consumers. So all of this, okay, from the 33 kV line to 415, they make up the distribution system. Okay, so now if you look at it clearly, this is the transmission system. So you see that the first component or equipment that you will see in the transmission line, okay, starting from here, is what? The step-up transformer or the transmission transformer. So as clearly shown by the voltage transformation ratio, it is meant to take the voltage from a lower level to a higher level. That is why it is called a step-up transformer. In this case, it is taking it to 330 kilovolts. That is the voltage that we transmit in this particular region or this particular part of the world. Okay, so this is an example of the transmission transformer. So here we have the power plant, and then the output from the generator is fed to the transformer, and then the transformer output, okay, they are connected straight to the transmission lines. So next to the transmission transformer is the switchyard. Remember, we said we must have a means of switching it, okay, from the generation station to the transformer, and also from the transformer to the transmission lines. That helps to switch the 11 kV. They are within the plant. Then after the generation station, then we'll be looking at very high voltage, 330 kV. Okay, so we have, in most cases, those switch jars placed outside. Okay, they are outdoor switch jars. So those switch jars, they make up what? The switch yard. The yard where the switching is done from the transmission transformer to the transmission lines. Okay, so as you can see, this is an example of a switch yard. You can see the circuit breakers. This is the transmission transformer. Okay, you see that the transmission transformer, the output, the input, as we all know, is from the generator. The output goes to these circuit breakers that are connected to your transmission lines. Okay, as you can see, they are connected to your transmission lines. So this is the transmission line. This is the switch yard, okay, because we have these outdoor breakers that is meant for switching. So these are the transmission transformers. Then these are the transmission lines that takes the 330 kV, okay, from this particular switch yard to the transmission lines. So these are what we'll see basically in the transmission system. So in the transmission system, we'll see, as we have it earlier, we'll see the first, the transmission transformer, which is a step-up transformer that will take it from 11 kV that is generated at the generation station to 330 kV. Then we have the switchyard in the transmission system immediately after the transmission transformers. So that switchyard there is where we have those circuit breakers and all other protective devices, okay, that are meant for switching the power onto the transmission lines. And then we have the transmission line. And then at the other end of the transmission line, we will have a step-down transformer that will take it from 330 kilovolts to 132 kV, okay? We also have switch jars, the ones that will receive the 330 kV before it goes to the transformer, and then after the transformer, the one that will deliver it into the 132 kV transmission lines, okay? So we have switch jars at the first substation, okay, in the transmission system, which is the switchyard. Then we have another substation at they call it the 132 kV substation. Then at the other end of the 132 kV, we also have the switch jars that will receive the 132 kV before it takes it to the another step down transformer that will take it from that 132 kV to that 33 kV, okay? So that is where the transmission lines actually terminate. We also have another set of switch jars that will receive this 33 kV and send into the 33 kV lines, okay? So here you see this is a complete power system showing the power plant, then the switchyard containing the transmission transformer or the step-up transformer that will take it in our case to 330 kV. This is the transmission line to the sub-transmission system, okay? Then further down, it is stepped down until we get to the distribution levels, okay? And to our ultimate consumer. So you will see that at every point of changing the voltage from one level to another, we have substations, okay? And the primary equipment or principal equipment in that substations, they are the transformers and the switch jars, okay? Now, back to what we said earlier, you can see that the voltage that is generated maybe at 11 kV, we cannot send that 11 kV, say, down to this particular substation, okay, where it is stepped down from 33 kV to that 11 kV. So now, why do we need to have this voltage stepped up? You'll see that the transmission system, as you can see, it is designed basically to reduce voltage drop. That is two things, voltage drop and power losses. Now let's take them one after the other. Voltage drop. You know that voltage drop from Ohm's law, which is V is equal to the current times the resistance on the line. And as you well know, all the power that is in the power system, okay, from that is generated at the generation station is taken to your load through those conductors. Are we getting it? Copper conductors. So these copper conductors, they all have some level of resistances. Okay, so once the power is on, that is there is load on the line, you will see that some level of current will be flowing on the line. Okay, and that current, as it is flowing through the line, definitely, since we have some resistances on the line, it will cause some voltage drop from that Ohm's law. V is equal to I R. So eventually, you will see that the voltage that we have at the end, where we want to use the particular voltage signal, may not be up to what we actually expected. Assuming, okay, let's say here now we need 11 kV, we are generating 11 kV here, okay? So assuming we are transmitting over a distance of some kilometers. So once the load starts coming into this particular system, you see that as the current is flowing, okay, back to the source of the power, you see that there will be some level of drops, okay, along all of these copper conductors or these copper wires that have some levels of resistance. It therefore means that if 11 kV is generated here, we will not have that exact amount of 11 kV here, okay, because there are some drops along the line. So that would mean that the more load we have on the network, the more drop we'll have on the system. And that is not a desirable condition, okay? We want to minimize the drop as much as possible. We want to have the required amount of voltage at the end where we actually require that. So if you look at these transformers too, you notice that you know that their transformation ratio, they are fixed. So if your input is low, definitely the output from it will be low. Okay? Which means if we are expecting 415 in our output, we may not have up to that 415 face to face. We'll be having, say, 300, which means a phase and neutral will be less than 180. Will be less than 180 fed to our load. Okay, so all of these, they are not desirable conditions, like we said earlier. So we need to minimize that voltage drop as much as possible. Okay, so how do we minimize that voltage drop so that we will not have reduced voltage at the other end of the power system? It is very simple. There we have the formula V is equal to I R. Okay, so if we can reduce the I, okay, we can reduce this I, what will there happen to the drop? The drop would drastically reduce. Are we getting it? So there are several ways we can do the reduction of this, but principally, okay, we want to reduce this by increasing the voltage supply, okay? That is increasing the transmission voltage, I mean to say. You know, the power in the system is constant because the power in the system cannot be more than the power at the power plant. Okay, I will know that power is a product of the voltage and the load, that is the current on the system. So since this is constant, we can only play with V or I. Okay, so since this is constant, if V is going up, I will do what? Will come down. If I is going up, V will come down. Okay, because both of them, they are inversely proportional from that particular power equation. So now we need small I because we want to reduce the voltage drop. Are you getting me? So for us to reduce this I, it means that we need to increase this, okay, so that this will be as small as possible. Okay, so if we have this to be as small as possible, it means that the drop along the transmission and distribution line will be small. Okay, so that is what actually informs the transmission of this voltage signal of power at very high voltage. In addition to that advantage, you will see that it also helps to reduce the power loss. Like we said earlier, all of these cables, they are made of copper wire, which have some level of resistance. I will know that power loss from this formula is a product of the square of the load or the current on the line and the resistance of the line. So if we are able to reduce this, since this is constant on the line, okay, though it is dependent on the temperature of the lines, okay, but since this is relatively constant, if we can reduce I, it means that we will be able to reduce this power loss drastically because it is the square, it is a product of the square of the current and the resistance. So if we reduce this by increasing V, okay, that means we also reduce the power losses. So another way that we can reduce the power loss is by reducing arrow. Okay, is by reducing arrow. So another way we can reduce power loss is by reducing arrow. And to reduce arrow, it means that we need to increase the cable size. Okay, so increasing the cable size will invariably reduce arrow because from the formula, arrow is equal to rho L over A. Since we are increasing the cross-sectional area A, you see that arrow, okay, since it's inversely proportional to A, will reduce when we increase A. That is the size of the cable. But there is a limit to which we can actually increase the size of the cable, or else the cable will become too heavy and more expensive for us to use, okay? So the best option is for us to increase V with the use of our transmission transformers, okay? And then reduce that V when we get to where we actually want to use the voltage. So that is the second way, but those are the two ways that we can actually reduce the power loss and the voltage drop. Okay, so this is the basic reason why we need the transmission lines, why we need to step up the voltage to that higher level, okay, for the transmission lines. It is basically to reduce the voltage drop and also to reduce power losses, okay? So if we are able to achieve this, it means that the efficiency of the power system will be increased. And that is one of our goals in operating our system efficiently. So we have seen the reason why we need to transmit at a very high voltage. So now we are going to look at the transformer, which is one of the major components in the transmission system. So, you know, the first transformer that we meet in the transmission system is the step-up transformer or the transmission transformer. Okay, so like the name implies, its major function is to transform the voltage from one level to another. That is the major function of the transformer. Then in this case, we are looking at the transmission transformer or a step-up transformer, which means that its function is to take the voltage from that 11 kV generated to 330 kV to be transmitted. So that component, that electrical equipment transformer, the transformer has some components. The major active part of the transformer is the windings. So the windings is where the transformation is actually done. And these windings, as you can see, they are wound on an iron core. Okay, so this is the active part of the transformer. But for the transformer to function properly, there are other parts also in the transformer. We have the connection bushings, okay? Since it's a step-up transformer, this is the high voltage bushings, and these are the low voltage bushing. On top of the tank is what is covering the main active part of the transformer or the transformer windings, okay? So when you also see, you see that we have a radiator-like structure on the tank or around the tank. These are meant for cooling the transformer. Since in the course of operations, because of the effect of I square arrow, power losses are bound to be around the windings of the transformer. And these power losses, definitely, they will come in the form of heat. So those heats, we need to take them out of the transformer. And that is where the transformer oil comes in. So the transformer oil, apart from doing the work of cooling the windings, it also helps in insulating the active part from the inactive part of the transformer. Okay, so let us see in a little detail each of these component parts of the transformer. So, like we said, the first part is the winding, and this is the winding. So on these windings, we have the primary and the secondary sections of the winding. So the input voltage, in our case, that the 11 kV comes into the primary windings, and this is the low voltage bushing. Okay, so the 11 kV will come into this low voltage bushing. Then the secondary winding, after the primary winding has been magnetized, since it is an alternating voltage signal that is sent into the primary winding, EMF or voltage will be induced in the secondary windings. So the 330 kV winding, 330 kV voltage, that 330 kV signal that is induced in the secondary winding is now connected to this high voltage or output bushings. Okay, so all the output terminals from the secondary windings, they are tied to these high voltage bushings. So the major active component, as we said, is the windings, and that is where the transformation is done. So when you also look, you see that we have the transformer core, okay, and then we have a former on which the winding is wound. So this core, its major function is to concentrate the magnetic field that the primary windings generate onto the secondary winding, so that we can have the most or the maximum induction as much as possible into the secondary windings of our transformer. So the other component that we want to look at now is the tank, and this is the tank. The transformer tank is what is housing the main winding. Okay, so the winding and the core, they are placed inside the transformer tank, as you can see. And also it's the part that also houses the insulating oil, or the oil that helps to cool the transformer winding. So the tank also, as you can see, also carries all other components, both protective and those components that are needed for the transformer to function properly, like the bushings, they are on the tank. The conservator, they are on the tank also. Even the radiators, the cooling fins, and what have you, they are all attached to the transformer tank. So we also have another very important section of the transformer, which is the cooling system. Okay, so we know that once the transformer is loaded, heat energy will be released. Okay, that is because of the I square arrow losses. So that power that is lost when the transformer is working, we need to remove them from the transformer, or else it may cause the transformer to degenerate to a situation where it will just fail. Okay, the insulation will complete the winding, the insulation of the winding will completely fail. So since we need to remove this heat, we need to have a system that will help us to do exactly that, and that is what the cooling system does. So the cooling system is a combination of the oil within the tank and the cooling fins, as we'll see later. So the heat generated around the windings, okay, being that the transformer oil is in contact with the winding, by conduction, the oil molecules conduct that heat away from the windings. So those molecules that have gained enough energy, okay, from the transformer winding, they will tend to move away, natural convection, move away from where they collected the heat or where the heat is being generated. So as they are moving away, cooler oil molecules will take the place of those hot oil molecules. So those hotter oil molecules, they will move, okay, to the tank body, and by conduction, they will give off this heat to the tank body, and then the tank will give off the heat to the surrounding or the atmosphere. That is how the radiator also works, because here we have cooling fins. These cooling fins, there are openings within it, okay? So the function is actually to spread thin the oil molecule so that we'll have as much surface area contact as much as possible, okay, with the fins that will conduct the heat away from the oil molecule. So as the fins conduct the heat away from the oil molecules, air molecules that are trapped around the fin outside the transformer, okay, those air molecules will now conduct the heat away from the metal, the material, okay, which will now be the molecules of the fin material, which will now be hot in the external. The air in contact with it, the air molecule in contact with it will conduct that heat away from the fins. So you see that with this kind of arrangement, the heat is taken from the windings through conduction by the oil molecules, and that oil molecule moves away to either the tank body or to the cooling fins, okay, and gives off that heat to the fin material, the metal used to make the fin. Then that heat conducted from the oil molecule into the film is given off to the surrounding air molecule, and then the air molecule will help to take the heat away. So that is how the cooling is done in the transformer. So we also have other protective systems that protects the transformer against excessive temperature. We know the effect of excessive temperature, as we stated earlier. Okay, so because of that I square arrow effect, as you are loading the transformer, the heat will degenerate to a stage that it can cause the breakdown of the winding insulations. And once that happens, it can cause turn-to-turn short or short to ground, as the case may be. So all of those, they are undesirable circumstances or situations that we do not want, okay, in our transformer. Then we also have protection system that protects the transformer against overload that will eventually cause overheating, and also that protects the transformer against shortage of cooling oil, okay, or shortage of transformer oil. Short to ground also, there are systems that protect the transformer against that kind of fault problem, over voltage, under voltage, and also internal faults within the windings. Okay, we have protection systems that protects the transformer against all of such. So we'll see some of them later in the course of this section of our training. So here are some of the components of the transformer that helps us to protect the transformer. So we know we have oil within the transformer, and we know that because of the thermal expansivity of oil, as it is being heated, it has that tendency of actually expanding. So once your transformer tank is filled with oil, as it is working, you know heat is generated. Apart from the heat that is generated, changes in the weather condition of the day can also affect the temperature of the oil. So once it is heated, naturally the oil will expand. So if the oil that is expanding does not have anywhere to expand to, that can cause overpressurization of the tank, okay, and may either cause explosion or may cause the compromise of this the gaskets that are between the cover and the tank, and that can cause serious leakage. So that is why this conservator tank is here. So the conservator tank is meant to accommodate the excess oil as it is expanding. So as it's expanding, the oil will now expand and move through this pipe to the conservator tank. Okay. So when the oil is cooling back, the oil in the conservator tank, all of them will now condense or shrink back into the main oil tank. So those problems that are associated with the expanding oil not having where to expand to will now be eliminated by the conservator tank. So that is the conservator tank that you are seeing there. Then another simple protective component that you will see in some transformers is the explosion vent. Okay, the explosion vent. So that explosion vent is like a relief valve, so to say, a pressure relief valve. So we know that if there are internal faults, there are some faults within the windings that can cause the generation of hydrogen gases. Okay, so as the oil molecule is disintegrated, hydrogen is formed, and that hydrogen, as it's forming, it moves up naturally. Okay, and we to pressurize the tank. So if the rate at which that hydrogen molecule is formed, okay, is very high than is higher than the rate at which maybe it is getting out somehow, either through the breather, okay, you will see that the pressure in the tank will build up to a stage that it can cause explosion of the tank. So the explosion vent helps us to avoid such a situation, in that the disc, the pressure disc around that vent will break, and then it will break and release that pressure, excess pressure from the transformer. So the issue of explosion will not be there. Okay. So the bushings, like we said earlier, is meant to insulate the active part from the transformer body. And like we said before, when there are some faults within the windings of the transformer, you see that that may cause arcing within the windings. And we know that arcing in itself is a very high thermal event, and that can cause the dissociation of the oil molecule, breakdown of the oil molecule, and thus generating hydrogen. That hydrogen, if it is not removed from the tank, will definitely overpressurize the tank. Okay? And if the tank is overpressurized, it will get to a level that it can either cause the gaskets between the cover and the tank to start leaking, or it can cause explosion. Okay, depends on the rate at which that hydrogen gas is generated within the transformer. So the explosion vent actually assists us in preventing such an occurrence or situation. So let us look at the windings in a little detail and see the reason why we need to cool the transformer winding. So as we all know, the transformer windings, they are made of copper wires, okay? So these copper wires, they have some level of resistance, as we acknowledged earlier in this training. So that resistance that the transformer winding possess, of course, when current flows through it because of the loading, there is bound to be some power losses, okay? So, and that power loss is what is given by this formula, I square arrow. So it is called the I square arrow losses. So as the current that is flowing through the winding is increasing, as you are loading the transformer, of course, the losses will also be increasing. That means more heat will be generated. So that heat, we need to remove that heat. So there are situations where ordinary air can actually do the cooling. That is, the air in contact with the transformer winding will conduct the heat away from the transformer winding. In some smaller transformers, that one is enough, okay? But as the transformer is getting bigger and as the loading is getting bigger, I is getting bigger, the power losses is also getting bigger. So we need a more effective means of cooling that transformer, okay? So that transformer that we use natural air conversion to cool is referred to as, the cooling system in that transformer is referred to as air natural or air cooled transformers. So now, since the power dissipated is, the energy dissipated is increasing with size and loading, we need a more effective means, as we said earlier. So we may now use either forced air instead of allowing the air to cool the transformer naturally, okay? So that's why you see some of these air-cooled transformers, they have fans that help to force the air through the windings. Then there are some, as the size is increasing, the loading is increasing, the heat dissipated is also increasing. So that forced air will no longer be effective. So we need more effective means. So what is this effective means? Is by immersing the transformer winding in oil, okay? So in that case, it's as we explained earlier, when we were explaining the transformer cooling system, okay, the oil remove the heat from the windings. So those oil molecules that are in contact with the windings extract the heat by conduction, and as they get heated up, they move away by natural convection to the tank of the transformer and gives all the heat to the tank of the transformer or the body of the cooling fins of the transformer. Okay, so when you look at it, you see that we have natural movement. The oil conducts heat by convection, by conduction, and then by convection, the oil molecule moves away. Okay, so that is a natural movement. So that is oil natural, and then the oil molecule now gives all the heat to the tank of the transformer, and then air molecule in contact with the tank of the transformer on the outside in the environment, okay, conducts the heat away from the transformer and also moves away for cooler air to come in. So that is natural convention too. So such an arrangement of cooling is known as the oil natural and air natural, which is called the Unang cooling. Okay, so this is the this is the cooling phase. This is the transformer winding. Okay, transformer winding, heat can be generated here, or the heat losses within the core too. Heat can be generated here. So all those heat needs to be removed. So the oil that is covering everything inside the tank conducts the heat away and moves into all of these cooling fins and gives the heat to the surrounding air. So this arrangement is known as, this is the complete transformer showing us the cooling fins, as you can see. Okay, there are openings within each of these cooling fins that oil can go into to increase the surface area of contact between the oil and the transformer, the fin or the cooling fin. Okay, so and this also serves as a means of trapping the air so that the air between these fins can conduct as much heat as possible from the fins as does radiators. Okay, so what we have just described is what is referred to as the Unang cooling. Okay, so on your transformer nameplate, you will see it as Unang. Okay, type of cooling or the cooling system is Unang. Oil natural, air natural. So this is the arrangement. The oil that is in the tank covers the transformer winding and the core. So as heat is generated, the oil molecule conducts that heat away from the winding. And naturally, by convection, it will move away from the source of the heat, okay, after conducting heat. You know, the molecule will not gain enough kinetic energy to move away. So cooler oil will come, so the hotter oil will move up, okay, and then the cooler oil will drop down. And then as it's moving away, it moves into the radiator fins, okay? And then in the radiator fins and on any part of the transformer too, it gives off that heat to the body of the transformer. And then the air around the transformer removes that heat from around the fins or around the body of the transformer. So we also have other cooling system too. Like we said, as the size is increasing, the amount of heat that is generated will also increase. So as that heat is increasing, we need a more effective means of removing that heat. Okay, so the oil natural, air natural may not be too effective. So we need to force air through the fins of the cooling system of the transformer, as you have in your car radiator. Okay, so these are the fans that you see, okay, that you are seeing here now on your screen. These fans, they help to either extract or blow air through the fins of this transformer. So as you are loading it, like on this case now, when the load is light, there may not be need for these fans to come on. But as you are loading it to capacity, okay, when we have more heat losses because of the I square arrow effect, okay, there will be need for more effective cooling, and all of this fan will come on, okay. So this type of cooling system is called the oil natural, because the air, the oil within the tank is allowed to flow naturally through natural convection, okay. So, and then the air outside is forced through the fins of the transformer radiator, or the cooling fins of the transformer. So this kind of cooling is known as the oil natural air force, because you are forcing the air, okay. So there are others where we may need more effective cooling, means we may need to force the oil, okay, through the oil pump. That is with an oil pump through the transformer windings, okay, as you can see here. So this pump actually helps to force the oil through the windings, then into the fins of the transformer. And then we also have air forced through the transformer radiator, okay, or the cooling fins. So you see that we are forcing oil and we are forcing air. So this type of cooling system is known as the oil force air force cooling system of your transformers, okay. So we also have the oil force water force, where the transformer oil is pumped into a heat exchanger instead of allowing the air, okay, to come naturally. We will now have, instead of air, we will have the oil flowing through heat exchanger that is cooled by water. So as it is flowing through the fins, the water that is flowing through the cooling water that is flowing through the heat exchanger, okay, removes the oil. It does not, it removes the heat in the oil. It does not come in contact with the oil. But so as you can see, the oil is flowing through a different channel within the heat exchanger, while the water is flowing through a different channel. So they don't come into contact. So as the oil is giving up the heat to the body of this tubing, okay, the water that is flowing through the external part of the tubing collects that heat from the external part of the tubing and take that heat out, okay. So this kind of case, especially when we have the oil forced through we have an oil water pump forcing the water through the heat exchanger, and then we also have an oil pump forcing the oil into the heat exchanger and also through the transformer windings. So such an arrangement is known as oil force water force cooling system. So you will see all of this on the nameplate of okay, so you see all of this on the nameplate of your transformer. So like we said, there are other protection systems on a transformer to protect the transformer against overload, which may be caused by excessively loading the transformer, okay, time more load than it can actually accommodate. So there are systems that when the transformer is overloaded, okay, can cause the tripping of that transformer. So such a system have components that look at the load on the transformer, okay, that is the current flowing through the line, the load on the line. And then if it is more than what it is set for, it can cause the tripping of the transformer. So we also have protection against earth fault. We also have protection against excessive voltage surge. We know that once there are voltage surges, what will be induced in the secondary will also, in the primary, what will be induced in the secondary will also increase. You know, it's a transformer, and the transformation ratio is constant. So when something very high comes into the primary, of course, what will come out in the secondary will be a reflection of what comes into the primary. Okay, so such surges can cause the destruction of equipment tied to that transformer or the line itself. Okay, since we are still in the transmission line, and even up to the distribution system. So we have a system that look at the voltage, okay, of the line that is through the, as we explained earlier, through the potential transformers. And then if we have excessive or we have voltage surge, it can send a signal to the circuit breaker to open the circuit up. So we also have faults, protection against faults in the tap changer. So because of the fluctuation of the input voltage, okay, that may result to also fluctuation of the output voltage, and we need a steady voltage output. So the tap changer helps us to regulate the output voltage. Okay, so once the input voltage increases, we tend to reduce the number of turns, okay, of the primary voltage that is supplied so that the output will reduce. Then if the output decreases, we increase the number of turns by increasing the tap, okay, the number of turns by changing the tap to a higher level, okay. So that will tend to increase the output voltage from the secondary. So internal faults too, as we'll see later, we have protection system that helps to protect internal faults within the transformer winding. As we'll see later, the Bucos relay, okay, helps us to protect the transformer against some of these internal faults. But on larger transformers, we have protection system tied to the windings themselves internally to help us to look at the windings, and once there are problems, it will help us to protect the transformer against such internal faults, okay, like the differential protection systems that helps us to look at the current that is flowing through each of the phases, compare each of them. So once there are shortages, you see that, or once there are excesses, or once there is a short of a particular phase to ground, you will see that, or within that particular phase winding, okay, that differential protection system will trip and protect our transformer against such faults. The incipient faults that are developing, we also have protection systems that protect the transformer against incipient faults. The Bucos relay is one of such that helps us, as we'll see later, okay? So as the fault is developing, the Bucos relay will give us a warning signal that there are developing faults within the transformer. So we have the thermometers that helps us to look at the temperature of the oil within the transformer, the temperature of the windings, okay, and also the temperature at the bottom of the transformer, okay. So all of these, they are means of protecting. So as the transformer is also getting bigger, we may have a need to have a gas analyzer on the system that will help us to analyze the gas, okay, that is coming out. That will give us a clear idea of what is happening, especially within the windings, okay. So those are some of the protection systems you will see. So we also have this is called the arc on, that helps to also protect against voltage surge or voltage spike that will be caused by lightning. These are for smaller transformer. On those bigger and transmission transformers, we have independent units on the line to the transformer that protects against surge. But the function of both of them, they are the same thing. So you see that this arcing horn, the upper part is connected to the live part of the transformer. Remember, this is a bushing. Yeah, this bushing is to insulate this live part from the body of the transformer, okay, or the non-active part of the transformer. So now, once there is, and then the other part of the arcing horn, okay, you see it is connected to the frame or to ground, okay, of the transformer. So between here and here, there is an insulation, okay, caused by air that is between that gap. Okay, so the dielectric strength of the air molecule between that is between the contacts of the arcing horn is strong enough to withstand the voltage to flow, or voltage to force charges or current to flow through to ground. Okay, so there won't, in normal condition, there won't be any flow, okay, because the insulation or the dielectric strength of the air molecule between these two is strong enough to withstand or to prevent such flow. Remember, air is active. So now, once there is surge, you will see that that surge, which is a very high voltage event, can cause the breakdown of the dielectric strength or the insulation of the air between these two contacts. And then once the dielectric strength of the air is broken down, you see that charges, okay, will be forced, or current will be forced through the other part of the arcing horn to ground. So once that happens, you'll see that that excessive spike or that voltage spike or excessive voltage will not go into the transformer winding. Instead, it will be clipped to ground. So that is how the arcing horn works. Okay, we have other, and that is how the surge suppressors or surge arresters in bigger units, that is how they work also. Okay, these are the surge arresters, okay, in bigger units. So it's the same thing. Once there is a spike, it causes the breakdown of the insulation between here and the ground that it is connected to. And then instead of it going into the transformer, it just flows into the ground, okay? So these are the surge arresters. Okay, we have three, one for each of the phases for larger transformers. So the other component that we want to talk of in transformer is the Buchholz relay. So the Buchholz relay, they are not in all transformers, especially the smaller units. You can't find them there. Okay, but as the size of the transformer is getting bigger, of course, we will need a better protection of the transformer, and it will be more feasible or cost effective to use the Buchholz relay. So you will find them in transformers that are very large, say as from 500 or 750 kV upwards, okay? So you find them there. So what is the work of this Buchholz relay? As you can see, it is connected between the conservator and the transformer tank, okay? Remember, as like we said earlier, what we said earlier, that the conservator tank is like a temporary holding unit for expanding oil. Okay, so during normal operations, as you load, heat is generated, the heat is conducted by the transformer oil. The transformer oil is bound to expand. So as it's expanding, like we said, if it does not have anywhere to expand to, it can cause the overpressurization of this tank and can cause the breakage of these seals, because these are the weakest points, okay? The seal between the tank cover and the tank. And that can cause leakages, okay? Or can cause explosion of because of overpressurization of the tank. So those, as the oil is expanding, it moves to the conservator tank. Okay. So once it cools, it contracts back into the transformer tank, the main tank. So the Bucos relay is always located between the conservator tank and the transformer main tank. So as the oil is flowing, rising from the main tank to the conservator tank, it always goes through the Bucos relay. Okay. So what is the function of the Bucos relay? So the Bucos relay, basically what it does is to protect the transformer against internal faults of the windings. Okay, internal faults of the windings. So we know that if there are shorts within the windings, like we said earlier, that can result to arcing. Okay, so it can result to arcing, and we all know that arcing is a very high thermal event, and that arcing can cause the dissociation of the oil molecule. And once that happens, hydrogen will be given off. Okay, so that hydrogen gas, as it's given off, it will rise from wherever it is generated. It will rise to the top part of the tank, and that will cause it to flow through to describe what, explain what we are trying to say. So now, as the gas, the hydrogen gas is rising, okay, from the winding through the tank, you see that when it gets to the Bucos relay, it will tend to rise up and not go through. Okay, so it will rise up to this particular upper part of the Bucos relay. So as it's rising up, there is a float switch. Okay, a float that is controlling a mercury switch at the up here. So as it's rising up, it will displace the oil, and then the float will drop, and that will cause the mercury switch to close. Okay, so as it closes, it will send an alarm signal to the operators of this particular unit that something is happening within the transformer. So that is for an incipient fault, something that is developing. So as the gas is accumulating, okay, the displacement will be happening, and then it will happen to a stage that the mercury within this upper part of the Bucos relay, the mercury switch, will be activated, and then it will send that alarm to operators. Okay. So now you will see that it is the gas, hydrogen, that displaces the oil within the Bucos relay, okay, and cause the float to drop to activate the mercury switch. In the case of incipient faults, not too alarming problems, okay? Then the other one is when we have a serious short, a serious fault within the windings of the transformer. So if you have serious problem within the windings of the transformer, you'll see that the arcing will be high. That means the heat generated will also be high. And as the heat generated is high, the rate of expansion of the oil will also be high. And the rate of dissociation of the oil molecule will also be what? High. So you see that the rate of rise of the oil and movement through the Bucos relay will do what? Will also be increased. So at the lower part here, there is a flap, okay, that that increased rate of oil that is flowing through the transformer will cause its movement or push that flap. So as it pushes that flap, it causes the activation of another mercury switch. Okay, that switch is tied to the trip magnet or the trip system, or to your breaker. Okay, your trip circuit, to cause the trip of your circuit breaker. So that is when a very serious problem is happening within the transformer. So you see that the transformer, the Bucos relay, is protecting the transformer against two kinds of problem. One is when an incipient fault, okay, is within the transformer, a fault is developing within the transformer. Then the second one is when a very serious fault is happening within the transformer. So other connection points too that are not properly made can also cause arcing. In that arcing can also result to the generation of hydrogen gas that can warn us of the fact that something is happening within the transformers. Okay, so that is the function of the Bucos relay, and you will come across the transformers that have Bucos relay along your power system, especially around your transmission lines and your primary distribution systems, okay, or your primary distribution system, yes, system in your power system, okay. So this is the Bucos relay, as you can see, okay. This is what you will see. So the input, this part, as you can see on the arrow, is connected to this part of the transformer, okay, that is connected to this part of the transformer tank. Then here to the conservator. That is how it is connected. So the last part of our power system is the distribution system. Like we said, in each section of the power system, we have our switch jars or substations, okay? So in the distribution system, we also have series of substations like that. So we acknowledged earlier that our distribution system starts from the injection substation, okay? Here we receive the 33 kV and step down the 33 kV with the transformer to 11 kV, okay? So that 11 kV will be sent to these switch jars, as you can see, okay, in the transformer, either it's in the substation, distribution substation. Then that, from this switch jar, it is now sent through to your distribution lines, okay? Then if it is within your facility, it is distributed directly from this switch jar room. So that is the distribution system, as you can see. So these are the distribution lines, okay, the 11 kV lines. So as it gets to where it will be used, transformers are needed to reduce it to the lowest voltage level of your distribution system, that is 415 volts, okay, face to face, or 220 volts face to neutral. So it is from this distribution transformer that the consumers, okay, now connect into their service entrance or their switchboard, okay. Then from their switchboard, they take to their various loads, as you can see here, to the motor control centers, where all the electric motors in the facility is tied to, okay. Then others to other distribution board that are controlling other equipment in the facility. Then others to other control panels that may be operating other facility equipment, okay, or production equipment, as you can see, okay. So this is the end part. Then if it is your home, if it is supplied to the home, of course, after the service entrance, then it is fed to various loads or units in that particular home. So this is the overview of the distribution system, which actually starts from the primary distribution level, okay, at the injection substations 33 to 11, okay, then the 11 kV, which is now sent to the distribution transformers that we have very close to the load. That is the last transformer to the load, okay, that now takes it to 415 volts to be used by those individual loads.